Hi, welcome back to Missing Chemistry. This is Electron Configuration of Selenium, SE lesson. Now, when we look on the periodic table, we find that selenium has the nuclear symbol of Se. So, we also notice that it is the 34th element in the periodic table, which means it has 34 protons for the atomic number. So we're going to write 34 right here. And right below the element symbol, we'll notice that it has another number, which we call the atomic mass unit. On the periodic table, it tells us it's 78.96. We don't have 0.96 on a neutron, so we have to round that up to 79. All right. Now, that means we have 34 protons, because that's what the atomic number tells us. And since all atoms are electrically neutral unless otherwise indicated, that means we would have to have 34 electrons. What about the number of neutrons? How do we figure that out? Well, that's pretty simple. Neutrons equal the AMU minus the number of protons. Well, that's not too hard. So N equals 79 minus 34 equals 45. Well, that was pretty simple, so we're going to put a 45 right there. Now, when we get ready to do the electron configuration, it's important to remember that in these energy levels, you have like S subshell, P subshell, D subshell, and F subshell. Well, the S subshell can only hold 2 electrons, and the P subshell can only hold 6 electrons, and the D subshell can only hold 10 electrons, and the F subshell can only hold 14 electrons. We're going to be using the off-ball principle, or the diagonal rule, which is this diagonal slide that you see here. We're going to start at the top of the slide, and we're going to keep going down these slides until we run out of electrons. And remember that we have 34 electrons. It's also important to remember that selenium Se ends in the P block. So that's a really important thing to remember. So now let's look at our electron configuration right here first, okay? So we start off at 1s2. Now we've used up 2 of our 34 electrons. We go back to the top of the slide, and we go down the slide again, and we use 2 more electrons, 2s2. Come back to the top of the slide, and notice that we have 2p and 3s there. So we use 2p6, 3s2. Now we've used 12 of our electrons, of our 34 electrons. Go back to the top of the slide, so we go 3p6, 4s2. Now, we come back to the top of the slide, and we notice that we have the D subshell there. That can hold 10 electrons, so it's 3d10, 4p4. And we stop because we run out of electrons. Okay, now our next type of configuration for electrons is our orbital notation. Now we're going to have to use Hund's rule. Hund's rule basically says that we have to use an up arrow in every subshell before we do a down arrow like that. So we have 2 in the 1s, so we go up and then down. Then we have 2s, so we go up and then down. Now there's 2px, 2py, 2pz, so there are 3 subshells in the P shell. So we go up, up, up. Hund's rule says put an up arrow in every subshell before you do the down arrow. You go down, down, down. You use up those 6 electrons, see that? And then 3s, up, and then down. Here we go again, 3px, 3py, 3pz. We go up, 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 then down, down, down. Pretty easy, huh? It's not bad at all. 4s, up and down. Now, we have our 3d10 here. So we have dx squared minus y squared, dxy, dyz, dxe, dz squared, right? So we're going to go 5 arrows up. 1, 2, 3, 4, 5, and then 5 arrows down. 1, 2, 3, 4, 5. And we used up 10 electrons. Now the last one, we have 4 electrons in that 4p, right? So we're going to go up, 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 and then we start the new one down. So that was really super duper easy. All right, now noble gas notation. So what the purpose of noble gas notation is to take these big, long electron configurations that look like this and shorten them down. So as you get further along the periodic table, this becomes more practical. So we have to find the nearest noble gas. Now you can't use krypton, which is after selenium, because it hasn't occurred yet. So you would have to go back to argon, the one before. So you put Ar in there. So if you notice that argon's noble gas notation and electron configuration would end in 3p6, right? So that means Ar represents all of this. Pretty snarly, huh? All right, now that leaves us 4s2, 3p10, and 4p4. Now you think you would write it that in that order, but no. The person who invented this says you got to put it in numerical order for noble gas notation. So you would be 3d10, 4s2, 4p4. Wow, that was pretty simple, huh? So last but not least is our quantum notation. So we have our N, which is our principal quantum number, our L, which is an angular momentum number, the M, which is the magnetic number, and the S, which is the spin number. Now the principal quantum number represents the number of which energy level that selenium is in. So it's an energy level 4, so we're going to write a 4 right there. See how that works? And since it's in the P block, our P block tells us that it has an angular momentum number of 1. See that there? Now remember, in the periodic table, on the P block, it goes -1, 0, 1, as you go across from gallium, germanium, and arsenic. And then, of course, selenium would be -1, bromine would be 0, and then krypton would be 1. But we're only going to selenium. So it's the fourth element over on the P block. So this is 1, 2, 3, 4. So it is going to be -1 for our magnetic number. Pretty darn snarly, huh? Now, last but not least, really important, our spin number is either going to be 1/2 positive, which represents an up arrow, or 1/2 negative, which represents a down arrow. Our last arrow that we put on our orbital notation right here is a down arrow. So this is going to tell us that this is going to be 1/2 negative. The really cool thing about quantum notation is that no two elements can have the same 4 sets of quantum numbers. Well, if you like this video, give us a like and consider subscribing so we can grow this channel. You guys be snarly, and we'll see you back here at Moosey in Chemistry!